Hello and welcome to week 6. So in this week we will talk about the large language models and the optimization in the training phase. So in this week we have 5 segments. So in the first segment we will talk about the foundations and few terminologies that we will be using across the segments over this 5 segment series. And in the second segment we will go towards the optimization in terms of mixed precision and numerical stability, and then in the segment 3 you will talk about the memory optimization and throughput analysis. In the fourth segment we will see the transfer learning for large language models. So if you have not done any transfer learning with the other models as such like CNN or any other models so far, that is completely fine. Here we will talk about how exactly is to be done and what is the transfer learning from the context of model training itself, and then we will apply it in the large language models. And in the last segment we will talk about the fine tuning, because fine tuning is the widely adopted training methodology in the large language models, and PFT or parameter efficient fine tuning using several techniques that we will see. One of them is LoRa, QLoRa is also there. So all these things we will discuss in detail in the upcoming segments. Okay, so here we will try to define the LLM first, what exactly it is, and distinguish the pre-training, adaptation and inference, because if you have seen the conventional deep neural networks, you have obviously seen the training, because we can train the model and we can serve the model or deploy the model for serving. So that means we train the model and use this for inference, right? In the case of LLMs, since this is huge in terms of the parameter size, in terms of the number of, let's say, layers or number of neurons that it has, that means in terms of model size itself it is large, and also in terms of the data corpus it requires for training, because obviously the large language models does not mean that large in sense of model size itself, but also the number of parameters, the model size as well as the data size that it requires for training, right? So now when you talk about the LLMs, we do not usually talk about training always. Okay, so that means we cannot train always the large language models as the sense we usually do for other deep neural networks like CNNs, right? So now here in this case, or any other machine learning model, so here due to this enormous size of the model as well as the size of the data parameter and the data size itself that is required for the training, we usually do pre-training and then we adapt that model and then we usually use for inference. Obviously training is one such case where you can do the training from the scratch itself, but we usually do not do. You take the pre-trained LLMs. Obviously we talk about what are the pre-trained LLMs that are available, where we can get them, which are open source, which are not open source. All these details we will see along the way, but now we get the idea that LLM training is not exactly the training that we talk about in training for other models like your ResNet, AlexNet or VGGNet and so on and so forth. Okay. Now for the LLMs, what are the different steps that we will see, and obviously we will tell exactly these differences between training, inference, pre-training and so on and so forth. So as I said, the large language models are large in the sense of the model, the size, right? And the large language models are the network which learns the probability distribution over the next token for a given prior context. Prior context in the sense that given a context or given a pre-tokens, let's say if I take a sequence of words, so that means the next word that I am going to utter that has the context of all these words that I have already spoken. So LLMs also are being trained to generate or to, let's say, predict the probability of next token, which is basically either the word or part of the word or several words together, given the context of the several other tokens based on the history. So this is basically the task of large language models, and here large means the very large parameters, counts, the data set, the training compute, also the compute, right, the compute capacity that we will need. Obviously, we will talk about the foundational models, foundation of model if we go for pre-training, when to go for pre-training, and how to shape the model, and how to adapt this for downstream or mainstream tasks that we will see. And also these LLMs are useful system and few of the techniques that we need to learn along the way, which is prompting. You might have heard about the prompt engineering, obviously, the RAG, the fine tuning, and so on and so forth. Okay. So the next token prediction, right? So it's always about next token prediction, next word prediction, or more scientifically, next token prediction. So what LLMs learn? LLMs learn patterns in text. So whatever text that we are providing to the LLM, the learning is basically the pattern that basically underlying many such distributions in the text that is given or any other data type for that manner, and it tokenizes or splits this text or given text. So in this few initial or foundational topics or the concept clearing slides, we will assume that the model is taking text input. Okay, it is not necessarily be always text as input for the LLMs, as you have already seen that you can give the LLM an image or video or audio as input. So input can be of any form. However, in this case, for better understanding, we will consider the input as sequence of text, and we can split that text into subwords, which is basically considered as tokens, and then the tokens are ID'd, that means based on the positions. Let's say all the tokens that or all the words that I'm speaking has its own position, and the position matters, right? So based on position, the complete context of or the meaning of the sentence can change, right? So the token IDs will be identified, that will be basically the integer indices or the positions of the tokens, and then the embeddings happen. So basically this is converting the text into a dense vector that is used by the subsequent networks that will be taking these embedding vectors and try to find the pattern in the given text. So LLMs do not see the raw text as the processing unit, but the embedding vector that we give or we convert from the text to token, then embedding vector. We will see how this process go through in the foundational models, and then after the vectors have been formed, then it is passed through several transformer model or blocks, which does the context mixing, and it happens across many layers. Okay. Talking about transformers, so transformers have the history from starting from the paper Attention is All You Need. So if you have not read that paper, you should read that paper. Obviously that talks about the foundations of the transformers and why the attention mechanism, which is the building block of any transformer model, have become so much popular, and which actually laid the foundations for the large language models over the years. And then the probability for the next token will be computed as the softmax. Softmax calculate the probability, and basically it is applied on the logits, which is the output of this all the different transformer layers, and then we get the token as output. Okay. So Tokenization defines the atomic units of the model, because the model will see these tokens, right. So, these tokens padded with or attached with the position, so that the position is also given as input to the LLMs, and then the embeddings will be happening for the vector transformation from the tokens, and then the context window will limit how many prior tokens that I want to see, because if I want to see the entire document, or I want to see half of the document, or I want to see the last few sentences, or I want to just see the first few words of this particular sentence to predict the next token or next word or next set of words, or based on how much length of the token is. Now, when I talked about this context window will see how much history I am looking at. That means how much history or how much tokens I am looking at the context or the back or the history. Token is basically the segment of the unit which is given as input, which has its own ID, which is basically the position of this token in this particular context or sentence. And training will repeat this pipeline over and over the massive data set, training data set, and it will see many positions also. Okay, so this is basically the basic idea of LLM, and the foundation is the transformer, as I said, right. So foundation is transformer, and transformer has the encoder and decoder layer, usually in the LLMs, which is ideally for just tokens to predict as the next, are mostly decoder based, like GPT based models or GPT like models, which has the decoders only from the transformer block. So, transformer has encoder and decoder. Encoders are usually used when we go for mostly the translation kind of tasks. So, if you have studied the encoder and decoder part, that is good, but here we will mostly look at the decoder stack, which is widely used in the as the basic block of the LLMs. Okay. So, here you can see we have the input tokens plus the positions, and then the must full multi-head self attention is there, which is the key ingredient of this transformer decoder block. So, multi-head attention learns different relations in parallel, right. So, like syntaxes, the semantics, the references, co-references, the code structure or whatever. So, relationship of these different tokens with all the other tokens in that particular context window is learned, the semantics are learned in multiple ways. That means each token, how they are related with other tokens in different manners. So, that way you have multi-head attention. We will see exactly the what computation goes on here, but let us talk about the next layers. So, next we have the addition and the normalization layer. So, basically the concatenation and normalization happens. Then the multi-layer perceptron, which will do the feed forward network, and then the another normalization layer happens for the next layer input. Okay, so this is the basic processes that goes through for the input tokens that is there. So, now each token will come and basically it will see the relationship with the other tokens through this self attention multi-head, and so in the end we will try to predict the probability distribution of the current token, which is xt, given all the other or previous tokens, which is x1, x2, x3 till xt minus 1. Okay, so this term represents all the previous tokens. Okay, so this is how we have the probability distribution or the estimation of the probability distribution of the current token given all the previous tokens. So, that is how the foundational LLM works. So, if you want to go through more detailed of the LLMs, you can go to this particular link for visualizing the transformer as well as the LLM. So here is one such visualization that you are seeing of Nano GPT, which has number of parameters of 85,584, which is very small one for demonstration purposes. You can go and see also GPT-2 XL, which has this many parameters. You can go also to see GPT-3, which is basically the model which has billions, even trillions of parameters, as you can see, and try to see exactly how these models work. And this is the GPT-2 small. We'll try to see how Nano GPT works. This will give us a glimpse of the stages that are involved in the computation, and essentially we will try to analyze the complexity of the computation that goes through and the data basically which is involved for this particular sets of computation, and try to understand the parameter computation, how these parameters number came, right. So this has around 85,000 parameters, as I said, and essentially here you can see these steps, right. So here you have the tokenization, where you have the breaking of the context or the given sentence into tokens. So you can see here you have how to predict. So this word is one token, these two words, so this is another token, this is another token. So this is the tokenization happen, right. So the tokenization is basically we call each of these inputs as tokens. So now based on what type of tokenization that we use, let's say you are using Unigram or any other tokenization that you are using, based on that actually the size of the tokens will be defined, and also for different models this varies, okay. So input is this, and you get the output as the token here, right. So this is the output token. So now this token are transformed. So this is the token along with the token embedding. So this is the token embedding and the position embedding. So these both will be added, as you can see, and you will create this input embedding. So this input embedding has the information about the token embedding. So token embedding is basically from this raw token to the vector transformation, and the position of the particular token for each tokens here, and then we have the these two embeddings mixed together, be it concatenation or any other transformations you can do, or you can apply over these vectors, and actually you can get this input embedding, which is basically again set of vectors based on the tokens that you have, right. And this particular input embedding goes into this your model here. So this is your attention. So as I said that the transformer block that you are seeing here, this is the basic building block of the the LLM, and after a few processing you will get the final output, which is basically your prediction for the final output. Now so this is one such transformer layer that you are seeing, right. So this is the transformer 0, this is the transformer 1. So based on that, how many transformer layers or transformer decoder layers you can have based on the model definition. You can have transformer layer 1, 2, 3. So here you have these 3 transformer layers, and then in the end you have the conversion of these logits into the softmax. Basically after the output of the multi-layer perceptron, another layer normalization will be applied, okay, which is obviously scaled one, and then the logits will be calculated based on the LLM, how many heads that we have had. So based on the channels we will create this concatenation or the aggregation, then the logits will be created. These logits will go through the softmax and basically will create the distribution, and we will see which is the highest having probability for this particular distribution, and we will take that particular token as the output. So this is how the LLM works. And talking about the embedding layer, the embedding obviously creates the sequence of vectors and create this embedding vector, and after the embedding, then the this embedding is passed for the, you can see this layer multi-head attention is going on. So now here we have how many attention heads? Here we have 3 attention heads. We will talk about that. So let's pause this animation and try to see what these heads are all about, right? So here you can see head 0, here you see head 1, and here you see head 2, which is 3 heads we are having. And each head we are actually taking this layer normalized value and converting into these q vector, k vector and v vector. Okay, so these are the 3 vectors that we transform based on the weights that we learned. So these are the learnable weights. So essentially all these are parameters, right? So for head 0 we have v weights, k weights and q weights to create this v vector, q vector and v vector. Obviously based on different heads we will have different combination of weights, okay, which will be learned across this training, okay. And here we have the q vector and k vector, which is basically creating this attention matrix, and then the, so here we are actually doing the dot product between these vector to get the embedding and the where attention weight you are seeing, right? So where these values are coming from, right? So embedding vector, which is the layer normalization vector, and the weights we are actually doing the dot product and getting these values. So q, k, v are made, and then the q, k, v will do the attention weight. So this is basically these attention weights which are being calculated, and then the v values will be, you can see this v value will be created, and basically this v value will be aligned with the qk, and these attention outputs will be calculated, okay. So these attention outputs are basically coming from your, you can see that query, right? So q, so this is your q and k the matrix multiplication, and basically you have the value vector, and basically this multiplication you are getting from to get these attention outputs, and these attention outputs you will go to this attention residual, because we are having multiple such layers, right? And in the last layer of, so all the layers, let's say here same, and in the last layer we are having the residual and then the layer normalization, and basically then the logits will be happening based on the LLM head weights. So you can see here 3 heads are there, and corresponding to that we have the head weights, which is crushing this entirely layer normalization vectors, all these vectors to this logit vector, and then we are getting this softmax. So this is how the foundation of the LLM works. Obviously now if we go for bigger LLM, essentially we will have the numerous number of heads and numerous number of transformer layers. As you can see here, how many such transformer layers are there, along with the so basically these outputs will go to different such heads, and for more matured LLMs you will have the layers increased in terms of parameters. So the size also will increase, and the parameter size will also increase, and the computation that is happening, which is the key computation for the matrix multiplication for your attention output, and matrix vector multiplication for your normalization or any other linear layer computation, okay. Okay, so talking about the layers, now the self attention layer which we just saw was kind of the key benchmark factor for laying the foundation for all these LLMs that are coming. So here parallelly all the token positions in a sequence will be processed together, and that's how we get the parallelization. And if you have thousands or millions of GPU cores, we can parallelize all these heads together, and you have seen that in the matured LLM how many such heads can be there, and basically this will create the resource limit in terms of training. Okay, so that's why the LLMs learn based on the large data corpora, right? So we have the website elements, the books, the codes, documents, and in the pre-training stage, so the LLMs are usually trained with $1 million of spend usage of GPUs, right? We need thousands of such GPUs to train these millions of multi-heads that are there, attention heads are there. So why we usually do not training or we do not train is that we have this constraint of using numerous number of GPUs at every time training. Okay, so we take the pre-trained, which is basically have the capability to predict the next token, and we do the tuning. Okay, so based on the base model or the whatever the base model that we have defined, that will be extracted from the pre-trained obviously the token prediction capability, and then we do the fine tuning. So fine tuning is basically done across the different LLMs that we have, and this tuning will define the training behavior of this particular model. Okay, so why fine tuning is needed? Because let's say we have trained one particular LLM with all the corpus, right? All the web data, all the documents, all the elements that are available in terms of PDF, in terms of text or whatever. Now when we deploy the LLMs, the domains shift. Let's say I am deploying my LLM for the for my medical application, or let's say for enterprise, or only for language, right? So that means the domain shift happens when we deploy the model, and whether we have to ensure through this LLM training whether we are satisfying the criteria or the accuracy for this particular domain or not, because this training happened on a general or generic corpus, and we cannot train on a large corpus of the medical data as such. So we have to do fine tuning, right? So fine tuning is required for better performance of these LLMs due to this domain shifting. And also this task format, whether we are applying it for classification, whether we are applying it for extraction only, summarization of the document. So some of the LLMs are deployed in organization which does only this job of summarization of the documents that are coming, right? Or chatbot, let's say I am deploying this LLM for only to chat, right? So what exactly is the task format? Whether we are only interested in classification, obviously it can be of different domain. Classification in medical domain is different, classification in let's say financial or fintech is different, right? We have the policy and style, so policies also can be different, whether we are deploying it in different continents. Based on the continents, our policies style will be different, right? And efficiency also change. So that's why whether we are trying to deploy it for a small scale organization or large scale organization, so what type of efficiency I need for that particular, so all these things will be addressed in the fine tuning approach or fine tuning methodology. So training memory is not only the parameters. So training is basically what? We have the gradients, we have to store the gradients. It's not only the parameters. So we have the gradients, activations. So these things we have seen. We have the large activations to be stored. We have to batches to be confirmed that we have the GPU video memory or video RAM to support that. So all these things need to be confirmed for training from scratch, but that we do not have. That's why we go for the fine tuning. And these adaptation strategies are different. So now we have these 4 adaptation strategies. One is prompting. Prompt engineering is one such strategy. There are no weights are changed. So all the weights that we have in the pre-trained LLM that are fixed, and this is very low cost because we just give the context of this particular conversation that will go, or the prediction that will go for the next token. We are giving proper context here so that it generates the next to token accordingly. So that is called the prompting. Obviously this is connected to your prompt engineering, and basically it is very quick because we do not need to change any weights. The RAG is another way of adapting the LLM which is already pre-trained for this particular domain, which is also called as retrieve augmented generation. So this is basically in cost terms, if we say it's low to mid, and the model weights stay fixed, but my external knowledge is retrieved based on fine tuning or at the runtime. So here fresh knowledge or private documents without training will be the best fit. So if we have, let's say, trained in 2024 our model, and I'm using that model in 2026, so all the documents between 2024 and 26 are not being seen by the model. So in that case I have to give the reference for the updated documents, and for those kind of cases the RAG is very important and performs better also. Full fine tuning or the supervised fine tuning or the SFT is all or most model weights are updated, mostly if we do full fine tuning. So that is the high cost. Obviously you can imagine how many GPU hours we need to spend, and this has maximum specialization of this particular domain. Obviously this is not always feasible, so we also go supervised fine tuning where we have the label data, and based on the label data we can fine tune few of the parameters for this particular LLM. Also if we want to update small trainable adaptations or parameters, we can go for PFT or parameter efficient fine tuning, and this is basically coming with a cost of medium cost because we do not need the full fleet of GPUs for full training. Rather we want to update here few parameters, and that way we will see how training can be done for this. So PFT also we will see in this particular segment. So in the upcoming segments we will exactly see how to adapt with different strategies of adaptation. Okay. So in summary, we have the large language models which are transformer based, and basically it works on the principle of next token prediction, given all these previous token as context, and it has the general capability to fine tune itself without even full training with several strategies that we have seen. And in these upcoming segments we will see exactly how to maximize the performance of these trainings or the adaptation techniques of these LLMs in the proper deployment. Thank you.